we earlier saw the work energy theorem, and now the work energy theorem gets modified if you have the case of a spring, because you can have two types of potential energies, right? So if we have any non-conservative forces, that means the work required to overcome non-conservative forces must be equal to the difference in the energy between the initial and final positions, right? So it's always going to be final minus initial that we're going to do. And you can do it for all types of energies, so for mechanical energies. So final minus initial kinetic energy, final minus initial gravitational energy, potential energy, final minus initial spring potential energy. Yeah? So it's got modified. If you have only conservative forces present, then our non-conservative work done is equal to 0, in which case the previous formula can be set as the total initial mechanical energy equals the total final mechanical energy. Yeah? This is our conservation of energy for the spring case. So if we have non-conservative forces, they must take up the change in energy, okay, since energy cannot be created or destroyed. So in summary, we have non-conservative work done, or work to overcome the non-conservative forces, is change in the different kinetic and potential energies, or we can rearrange and regroup our two final energies together. Yeah, so this is total final energy minus total initial energy. That must go into the non-conservative work. So let's look at a problem. 0.1 kg toy car is propelled, here's the car, is propelled by a compressed spring as shown. The car follows the track that rises 1.18 meters, that's here, that's 18 centimeters, above the starting point. The spring is compressed 4 centimeters and has a force constant of 215 newtons per meter. That's the value of K. Assuming work done by friction to be negligible, find how fast the car is going before it starts up the slope. So right here, okay, before it starts going up the slope. And how fast it's going at the top of the slope. So we have one position here, one position here. And we have the spring that starts off the car. Okay. So how do we tackle this problem? We're going to apply conservation of energy. There are no non-conservative forces mentioned, so we're going to assume, because it says friction is negligible, we're going to assume there are no non-conservative forces. So at my initial starting point, the car is not yet moving. The energy is stored in the spring. How much energy is stored in the spring? Let's see that. So if we wanted to write down the potential energy of the spring, let's go. Potential energy of the spring, how do we write that? Yeah? So that's going to be 1/2 kx squared, where x is the displacement of the spring. Yeah? So we know that the spring was compressed by 4 centimeters. We're going to convert this into meters. So 0.04 meters times 250 newtons times half. This is the total energy at the start. As soon as you let go, this energy gets converted into the kinetic energy. If we set our potential energy on this line to be equal to 0, and I'm going to write that here. So we're going to set the reference of potential energy. Remember, that's one of the first things you have to do in energy conservation programs. I'm going to set it 0 at this point because our height is measured from here. That's a good point. That means the car has no potential energy. So the car has only kinetic energy at the start, and that's going to be given by the formula for kinetic energy, 1/2 mv squared. If we know the mass of the car, and that's given as 0.1, so we can equate these two so that all the energy stored in the spring goes into the car. Yeah? And we can calculate the value of v. Right? That's my initial velocity of the car. So that's what's asked in part A. That's how you're going to do part A. Part B, how fast is it going at the top of the slope? So now we know the initial energy of the car is. It's this 1/2 mv squared, right? After we've calculated V, which is the same value as this. And since we only have conservative forces, that must equal the energy here. Okay. What is the energy at the top? At the top here, what kind of energy do we have? We have potential energy given by mgh, yeah? And we have kinetic energy too, because the car is still moving, 1/2 mv squared. And let's write this as some V final squared, just so that to differentiate this from this initial velocity. So let me write this as VI. So the sum of these two terms must equal this number here, 1/2 kx squared. Yeah. Let's just make sure that everything is known here, and there can be only one unknown, which is this velocity that we need to find. We know n, we know g, which is a constant. We know this h. Remember to convert it into meters. So indeed, we can find the velocity vf using all of these equations. Let's have a look at it. So this is part A, 1/2 kx squared set equal to 1/2 mvi initial squared for the car before it goes up the slope. We solve for vi, and it's going to come out to be 2 meters per second. Okay? And then part B, when it's up here, so 1/2 mvi squared, the initial energy of the car. We're going to insert this value. The initial kinetic energy of the car equals initial total energy equals in final total energy, mgh plus m. So we have mvf squared. The m's cancel out. We're going to insert the values here now. Quite self-explanatory. We're going to solve for vf squared, and it'll come out to be 0.68 meters per second. So the car has slowed down as it has gone up here because some of its kinetic energy has been converted to potential energy. So if this value had come out to be greater than 2 meters per second, I would be concerned. I would feel, how could it be going faster up here? If it had come out to be equal to 2 meters per second, also you would be concerned, then where did this potential energy come from? Yeah. So this is the kind of check you need to do when you finish a problem.